Today is November 16, 2021, and we are going to do the experiment on moment of inertia. Tuesday, right? Today is Tuesday. We're going to do this experiment on Tuesday, that's 16th, and on Thursday as well, which is the 18th. Okay. So today is lab number 8. And I need you to download the spreadsheet that you have before, not just download it. You must have already have the spreadsheet in your hard drive. If you have the spreadsheet in your hard drive, just rename it. Okay, here you go. It should be P37 for the Tuesday students. You rename it as a Tuesday, Lab 08, and you put your group number here. My group number, since I don't have a group, I put it group 0. If you have group 1, you put 1 in there, 2, 3, and so on, right? You open the spreadsheet, lab number 8. You should have this spreadsheet that you see right here. That's the moment of inertia spreadsheet. Don't forget to fill up your group number, student name. Don't make any modifications here other than just logging the data here. Don't do not add lines, do not delete lines, do not add columns, do not delete columns. I need you to preserve this format and only input your data, okay? So let me go through this experiment with you. So you know what you have to do. Okay, so here you go. Here's the first slide of the experiment. Here you go. Moment of inertia experiment. Moment of inertia first part. First part is constant radius and variable mass, just like we did in the centripetal force experiment. We're going to do this moment of inertia experiment with constant radius, variable mass, and then the next one is going to be constant mass and variable radius. We start with the Senko centripetal force apparatus, like we had before. Rotating shaft, indicator rod, the pulley there. Okay. And what you're going to do, you're going to measure the diameter of the rotating shaft. You need that. You need that to find out the torque that is applied to this rotating shaft. Okay. So here you go. That's come our first, the equipment here that you're going to be used, right? One is going to be the centripetal force apparatus, and now you're going to use the micrometer to measure the diameter of the rotating shaft. That's the resolution of my micrometer in millimeters, hundredths of a millimeter. And what else do you have? Let's go to our spreadsheet here. See, in your spreadsheet, you are going to fill up the value of the diameter of the rotating shaft. Not only the diameter of the rotating shaft, but also the acceleration of gravity. Don't forget that, right? There will be other data that you have to put there, but let's stick to this one for now, so you don't get overwhelmed by the amount of data. Okay. What else? Going back here, you measure the diameter of the rotating shaft with the micrometer, and you're going to insert a threaded rod. I'm providing you with a threaded rod that fits there in the tip, in the top of the rotating shaft, and that's going to be added here to the list of equipment. I want you to align the center of the threaded rod with the center of the rotating shaft. So whatever distance you have on the left side is equal to the distance you have on the right side, middle of the threaded rod, right? You have a locking bolt that you're already familiar with. Let's put that in the list of equipment. Locking bolt. Already comes with the apparatus, the centripetal force apparatus. I'm gonna abbreviate that centripetal force apparatus as CFA. Okay, comes with the CFA. In the next one, we are provided with the wing nuts. You're provided with a total of 4 wing nuts. So you put the wing nuts there in the thread rod in this configuration on the left side, right? And you're gonna put on the right side as well. So I'm gonna write down here 4 wing nuts. Next thing you're going to do, you're going to get a slotted mass, 20 grams slotted mass, and I'm going to measure its weight with the scale. So here you go, slotted mass, and there will be several slotted mass there. The 20 grams is just one of them. You're going to need also a scale with the resolution of 100 of a gram, right? 100 of a gram, which would end up being 1, 2, 3, 4, 5 kilograms. That's how you write down your weight. Since it's at 20 grams, let's put 3 here. Micrometer, since it's millimeter here, you might need another decimal place, another significant digit there as well. And don't forget to change that, the measurement of the micrometer, with 1, 2, 3 in meters scale. Okay. So we go to the spreadsheet and we log the value that we got with the scale right in here in this cell. So far you have measured the following. You have measured D and M. G, you already know, is 9.8 meters per second square. You can log in there. Make sure you log the 9.8 here. It's not a measurement, but it's a result that we got from a previous experiment. One of the first experiments that we did there in the classroom. Scale. Next, we get the 20 gram mass and we clamp it between the 2 wing nuts in the threaded rod of the rotating shaft. Now you measure the W. Just put there a note in your own data sheet. You don't have to put that in the spreadsheet. There's a reason why, it's not going to affect our experiment, the W, but it's a good thing that you keep the value of the thickness of your rotating mass handy there for you. There's a reason. It's going to become clear why. Now you have to measure the radius of rotation of the rotating mass from the center of the rotating shaft to the center of the mass, of the rotating mass. Students usually make the mistake of measuring the distance from the center to the edge of the mass. Students make the mistake. Don't measure to the edge. You gotta measure to the center of the rotating mass. So let's go. Here you go. You're gonna use a ruler, regular ruler, with a resolution of a millimeter, right? When you change that to meters, you get this number of significant figures. Now, the R that I'm talking about goes right in here in the spreadsheet that I provide to you. In the next step, why did you measure the W? There's a reason why you measure the W. You have to make sure that for this mass to behave like a point mass, this moment of inertia is going to be mr squared, okay? In order for this mass to behave like a point mass with a moment of inertia mr squared, the radius should be at least 5 times the width of this mass. If the mass is thicker than that, then the mass is no longer going to behave like a point mass. That's why we measure the W. The W doesn't affect our experiment, provided you have a radius that's greater than 5 times the thickness of the mass. We are going to clamp a second slotted mass, okay? The same distance from the center. And I'm gonna get that here, slotted mass, 2 has to be 2 20-gram slotted mass. You're gonna need more than that. So let's start with this one first. You're gonna need a string, 1.5 meters long string. Let's log there. Here you go. String 1.5 meter long. And you're going to wrap this string around the rotating shaft, just like you have that here. Okay? You're going to wrap like 0.8 meters of this string around the shaft. Since you're going to measure this string, you're going to need also to have a meter stick. Okay? Once you wrap it, make sure you keep the string as horizontal as possible. You have to minimize this angle of the string, okay? You won't be able to make it completely equal to 0, but provided you minimize it throughout the experiment, would be great. So what's happening here? What else we have to do? Let me show you what else we have to do. This string here is applying a torque to this shaft. That's what's happening. It's going to apply a torque. It's not is applying. It's going to apply a torque to the shaft. How it's going to apply the torque to the shaft? We're going to apply the torque to the shaft by hanging a mass there at the end of the string. You get a mass, hanging mass. Go. Hanging mass. We usually use a 100-gram hanging mass. Measure the hanging mass value, right? And we log right in here. Okay, if you're using a mat hanger, this M includes the net mass. So 1, 2, 3, 4 raw data, right? And you hang your hanging mass there, the hooked mass, lowercase m to the end. So it's this mass that's going to apply a torque to this rotating shaft. Okay, and we're going to release this hooked mass. Is going to accelerate, and you're going to provide an angular acceleration to the whole set here. And with this data, the time of fall of the mass, we will be able to determine the moment of inertia of our system, the moment of inertia of the 2-point masses. So that is going to be the next one. Here you go. Do you see here? The mass start there at the top, and it should touch, the string should be long enough to make the mass reach the floor. 1.5 meters should be enough for that. Unwind the string around the shaft until the hanging mass touches the floor, right? Make sure that the string is long enough. When the mass touches the floor, ensure there is still 1 or 2 turns around, the shaft. Okay, so right in here, 1 or 2. Check the angle that the string makes with the horizontal. If this angle is too steep, rewind the string to minimize it. You don't want this angle to be too steep. Why is that? If you make this angle too steep, then the force that applying the torque here to this rotating shaft is not going to coincide with the mg. Okay, so by minimizing this angle in the horizontal here, you ensure that the force applying the torque to the shaft is equal to mg. That's why you have to minimize this angle. The angle the string makes horizontal must be minimized throughout the whole experiment. It's impossible. Ideally, you should make this angle equal to 0, but it's impossible. It's impossible to make this angle equal to 0. Okay. And one more important thing. Let's go back here. When you wrap up the string around the shaft, you must have a single layer of the string. You cannot bunch up 1, 2, 3, 4 layers of string, one on the top of the other, because if you do that, you're going to change the torque. Okay, you're going to change the torque. So make sure you have just one layer of string wrapped around this shaft, so the torque is always the same. What else you have to do? Bring the mass as high as you can. Bring the hanging mass as high as you can, and measure the height h. Measure the height h from the bottom of the mass to the floor. H is measured with either the meter stick or the ruler. Okay, so here you go. I'm going to the hanging mass will be recorded as being in grams, right? 12312 grams, which is equal to x 12345 kilograms. That's how you're going to record the hanging mass. Height of the hanging mass is measured with the meter stick. So it's going to be around 1 meter. It's going to be in centimeters, but then you got to change to meters. 1, 2 millimeters. Yeah, like that. Height of the hanging mass. Before releasing the mass, make sure the string wound around the shaft forms a single layer, just like I mentioned. If 2 or more layers of string accumulate around the shaft, the torque applied to the mass will change and will not get a good experimental result compared to this theory. Hold the shaft with the hanging mass at height h. When you're ready, release the shaft and start your timer. Again, just like before, to prevent any reaction time error, whoever releases the mass and that's the timing is the same person. Do not split the task. This mass is going to fall, right? And you're going to measure how long it takes for the mass to reach the floor. That's going to be your T1. You're going to repeat the experiment 3 times, just like here. You go T1, T2, T3, and don't forget you measure the height as well. That was done for the 20-gram mass. That was done for the 20 gram. Repeat this procedure twice, another 2 times for a total of 3 measurements, right? T1, T2, and T3. And then you're going to repeat for 50 grams, 70 grams, 100 grams, 120, 150. So this lot with slotted masses, right? All this time you're going to be using. Cool. So here you go. Slotted masses: 20 grams, 50 grams. What's next? The 70 grams, you're going to combine 150 with another one of 20. Okay. You're going to need 100 grams as well, 2. The 120, you're going to combine the 100 with the 20 grams. And the 150 is going to be 100 with the 50. So all you need are those 6 different slotted masses there for your experiment. And hiccup. So here you go. That's 20, that's 50, that's 70, that's 100, 120, 150. The last one is a special one. The last data point that we're going to get is a special one that's going to be done without any slotted masses. You're going to take out the slotted masses from the wing nuts. You are going to make sure you get, you're going to get the 2 wing nuts together. Make sure the point of contact of the wing nuts are at the same distance that the other mass are, right? And you repeat the experiment. That's what the last one is all about. Thank you, sorry. 0 grams right in here. You log 0 grams. So let's do that. Here you go. Well, you know, right? I'll let you do that. Here is going to be 20 grams, 50, 70, again, 100, 120, 150, and 0 grams. So those cells are the cells for the raw data, and that's what they want. Those are the data. This is the data that you have to write down in your data sheet for me to sign at the end of the experiment. Everything else is calculated. Here we take the average of those 3 values, of those 3 time values. The moment of inertia is calculated according to the data that is provided. This moment of inertia here was derived in my lab manual and also was derived here in this note that you see here. Okay, here you go. That's not the derivation. The derivation comes from right in here. We use arguments of conservation of energy to find out what is the moment of inertia. Okay, so what do? We start with the potential energy of the hanging mass. That's the initial potential energy. The hanging mass is initially at rest. The rotating shaft is initially at rest as well. And this potential energy must be equal to the kinetic energy of the hanging mass just before it strikes the floor, plus the rotational kinetic energy of the shaft with the masses and the wing nuts. So what we do next, we calculate the moment of inertia from this equation. Okay, here you go. That's the angular velocity. That's the linear velocity of the mass. And we have a relationship between those two because the shaft is rotating without slippage. The string that's attached to the shaft is not slipping, right? So the relationship between the velocity and the angular velocity is related to the diameter of the shaft. That's why we measure the diameter of the shaft. I am writing down the angular velocity in terms of the linear velocity and substituting it right in here. Okay? What you see here is nothing more, nothing less than what you see right in here. What else? What else? We have to write this equation in terms of the measured parameters. We know m, we measure d. We know m, we measure d, we measure h. We know g from previous experiment, but we still do not know the final velocity of our mass, final linear velocity of just before it strikes the floor. But it is possible to find out this velocity, this final velocity. How do we do that? Okay, we go under the assumption that the motion of the hanging mass is uniformly accelerated, which makes sense. The mass of the hanging mass doesn't change, and the tension in the string doesn't change either as the mass moves. Because of that, we can write down the average velocity as being the final velocity plus the initial velocity divided by 2. Because the initial velocity was 0, we end up with this equation right in here. But there is another relation. There is another relation for the average velocity. The average velocity is delta y over delta t. Delta y is h, the delta t is t average. We made 3 measurements of the time of fall, remember that? T1, T2, T3, and we have the time average out of that. Make this one equal to this one. We get the velocity, substitute right in here in my original equation, and now we finally have an equation for the moment of inertia in terms of the measured parameters. Okay, I can simplify that. It's just a matter of doing mathematical manipulations here now, because the trick was this one here. T average, blah, 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 and that's what we get. This formula is the one that you see there in the spreadsheet. Right in here in the spreadsheet. Okay, but let's not forget that this is the moment of inertia of the whole set. Is the moment of inertia of the shaft, the crossbar, here you go, the wing nuts, and the masses. I want to know only the moment of inertia of the masses, which behaves like a point mass. They behave. How do we find that out? How do we find that out? Okay, I'm gonna need another drawing here for you. So here you go. I'm gonna copy this guy right in here. Remember that the moment of inertia is a scalar quantity. Okay? I don't need everything here. All I need is the drawing of my, here you go. So what do we have here? The moment of inertia of this guy, which I call I. Here you go, I. Which, by the way, is the one that will be obtained with that formula, is going to be given, and I'm going to put an equal sign here, right in here. Okay, that's going to be given by the moment of inertia of the two masses, the 2-point masses that I call, in my book, I call it IMR. Okay, just nothing more. And by the way, I'm going to do the following. Here you go. I'm going to make this guy look like a ghost, so you understand. I don't need that. And the The wing nuts has negligible moment of inertia, by the way, but I'm gonna put them in grayish color. Grayish color with like that, grayish color. Plus the moment of inertia. Whoa, we're running out of space here. Moment of inertia of this guy right in here. And this one is going to be like that, okay? This one I call IMR, which is the one that you want to find. Should be MR squared. And this other one I call the I naught, which is the moment of inertia that we measured without the masses. Subscript. Okay? Let me get this guy here. Oops. Like that. We calculated from that equation that you saw, right? I naught is the I calculated for the mass 0, rotating mass 0. So that's my I naught. That's my I naught here, and that's my I. And here is my IMR. This is the one that should be close to MR squared. Okay? So here we go. You see that? I minus I naught. Everyone here is I minus I naught. I minus I naught. And that's what this equation is telling us. Okay, this equation is telling the following. I'm going to write down the equation explicitly in a mathematical format. Equal I naught. Okay, we solve that for I naught. That is the one that we want to find out. Minus right here. Here you go. That's what we get. So that's what we have for today's experiment. Oh, with just one more thing, right? You have to plot IMR. You can have all the against the value of the rotating mass. Go to the, if you do something like that, you are supposed, here you go, going back here, here you go. You are supposed to get what? You are supposed, if you plot IMR in the y-axis and M in the x-axis, you're supposed to get a straight line with this slope right in here. And that's the slope that you have to put right in here in this equation, in this table. Watch out for the delta, which is the percentage difference. The value of 2r squared, theoretical value of 2r squared, is calculated directly from here with constant r. So next time we are going to perform the same experiment, but instead of changing the masses, we are going to change the radius of rotation. Okay? So hope you have a good day, a good experiment, and I'll see you soon. Thank you. Bye bye.